Hey YouTube, welcome to this epic new episode where I show you how to implement pathfinding into your game using A star. If you're like me and you love building your own game mechanics, you've come to the right place. If you enjoyed this episode, leave a sub and a like. This video took a long time to make. Firstly, I'll explain with an animation how A star briefly works. Then we'll get right into the coding by making a node graph, which will be the foundation of our A star script. After that, we'll code the algorithm itself, which I promise you isn't that hard when we follow some simple pseudocode. Once we can get our path easily, we'll make our player follow that path and display the path in the gizmos. Right now, I'll show you the finished product. Let me play the project. Firstly, the yellow lines that appear is an indication that our node graph is set up. Then all we have to do is right click in the game view and our player will follow the path to the target. The red lines indicate the path that the player has been following. The best part is that you can move the target and right click again and the node graph will reinitialize and find new neighbors, and then the player will be able to find its way back to you again using the shortest path every single time. Now I'll jump into the explanation of how A star works. Enjoy the rest of this video. Guys, welcome to the explanation of how A star works. So how A star works in my project is I have the obstacle and I place nodes around it, essentially creating a boundary so that the player doesn't go through the obstacle. The rule is that the player can only traverse on nodes, so it has to go on top of nodes. And since there are no nodes in the middle, it can't go through the obstacle. But you might be thinking, well, what if the node had a connection between here and here? This would make the node have a connection through the obstacle, which would therefore make the player go through the obstacle. But no, how it works is we have neighbors. So this connection would not exist. Why this connection would not exist is because we would send a raycast, and this raycast would hit this obstacle, and that's not a node. Therefore, the program will be like, okay, well, that's not a neighbor. But then it will raycast to, for example, this node here, and it does hit it, so it's a neighbor. It raycasts to this one, it is a neighbor. So then all the nodes raycast to each other and find their neighbors and make essentially what is called a node graph. Okay, so now that we have a node graph, so let's visualize the node graph again here. So we have an N, 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 and the lines are a connection between two nodes, the neighbors. Okay, and the start is a node. Okay, so the node has a connection to the start, and start has a connection to the node. The end is a node as well. So this is how our node graph is going to look in our example that I'm going to make soon. Right, so how this then chooses what nodes you want to pick is using a variable called fcost, and this, the lower the fcost is, the more the more you want to go towards that node. So for example, the fcost of this node would be 4. How would I know that? Well, the distance between the node and the end might be 3, and the node and the start might be 1. The fcost is basically those two values added up. Okay, so the fcost of this node might be 4, this node might be 4, and essentially all of these nodes should be 4 if they're all symmetrical. Okay, well, okay, now let's imagine the fcost for all of them. Okay, so we have node, 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 4, 4, 4, and 4. Okay, so start and end. Okay, so we pick out of these two because these two are the neighbors for the start. Okay, since they are both the same, we go to look something for the h cost. And the h cost is the distance between the node and the end. So these two will both be 3. And since they're both the same, we pick one out of random, okay? We pick this one, for example, okay? Now, we put the start node into something called the close set. So this node here won't be able to go back to the start, okay? This node can only select out of this and this node. Alright, so the f cost of this is 4 and the f cost of this is 4, so both are 4. Okay, so how do we pick now? Well, we check the h cost again. The h cost of this node is only 1, but the h cost of this node is 3. Therefore, we pick this node because it is the better option. Now, we check between this node, the end, and this node, and this node. Well, the f costs are different this time because this is the end. Therefore, the f cost will be something like 4. Again, the f cost is the same, I'm sorry. But the h cost is obviously going to be equal to 0 because it is the end. Therefore, this node is selected. Therefore, this node is selected. And that is the end. So we know that the end is picked right now. Okay, so how do we retrace the path back to the beginning? So this is how we retrace. Okay, so let's imagine that we have already calculated f cost and we know where everything is. We know the value of everything, alright? So first we've picked this, then we've picked this, and then we've picked this. Okay, so how this works is when you pick this, there is something called the parent variable, okay? This will be stored in a dictionary. So the parent of this node will be equal to the node before it. The parent of this node will be equal to this. And the parent of this node will be equal to this. Okay? Then all we have to do in the end is we have to retrace our steps. So we have to look at the end node's parent, which will lead back to here, and we have to look at this node's parent, which will lead back to here. We have to look at this parent's node, which will lead back to here, and then all we have to do is create a list. So the list would go like this. List end, and then we'll call this n1, n2, n3. So the list will go n1, n2, and then the start, okay? This is our list, basically, and all we have to do is reverse it, and we'll get start, n2, n1, and end, which is basically our path, which then our player can follow back to the end. So if it follows this path, it will give us this path. Alright, that's how easy A star is. And now we'll hop into Unity and start making the node graph. Now that you've survived through my daunting explanation of A star, let's set up the scene to begin our node graph. Okay, so I've created a new project in 2D, and I've created 3 new folders: prefab, scenes, and scripts. In my scene, in my scenes folder, I've saved the scene and put it into that folder. In the prefabs folder, I've created another folder called sprites, and inside that I've got 3 objects. I will teach you quickly how to make these objects inside Unity. Okay, so all you have to do to create these objects is create sprites square. Okay, we're gonna name this our obstacle and node. Okay, so this can be our obstacle node. Okay, and we're gonna go sprites, and I'm going to go circle, I'm gonna go player and target. Okay, so I'm not gonna waste too much time with the design. I'm just gonna go 0 0. Okay, and I'm gonna create empty underneath this, and I'm gonna create underscore node. Okay, I'm gonna create an empty here and called A star. And I am telling you guys, you need some basic knowledge with Unity before you really start doing this. It's a bit complicated, but okay. Here we are going to quickly set up our obstacle right here. Okay, that should be fine. I'm not going to use a box collider 2D. It's a bit complicated to use it, but I'm just going to use a normal box collider. Set the Z to 1. Okay, size Z to 1. For the player as well, I'm going to use the box collider 1. You can do much more like detail later, but that's not what I'm really aiming for. This is my player. Okay, Command D. duplicate, and this can be our target node. Alright, now we need our nodes for the obstacle. I'm not gonna leave all of this white, but yeah, I will change it. Okay, so we need 4 different nodes. Let me just quickly do that. Alright, here are our nodes. You know what? Yeah, that should be fine. I'll give it a good gray color, and this even like a grayer color. Okay, the finish can be a nice decent blue color. Okay, and the beginning can be a nice simple green color. Okay, once that is done, we should be able just to finish up. That's our setting up. Actually, well, I'll add one more thing on all of these. I'm just gonna add a simple node script. Easy, we're done. Okay, now it's time to make the node graph. Open up the node script and let's start. Okay, firstly, we're gonna add a using system.collections.generic. This will enable us to use the list function. Okay, now let's make a hide inspector so we don't see this in the inspector, and we'll create a public list of nodes called the neighbors. Okay, and we are going to just initialize it. Alright, now we're going to make a public void called find neighbors. Okay, and we're going to just go neighbors equals new list of nodes. We're going to clear it every time. Okay, so after we do this, we're going to go for each node and in game object of find objects of type node. This will find every node in the scene. Okay, now ray equals new, so transform the position. So we're going to create an array that goes from our node to the node that we're checking right now. The direction is going to be the simple n.transform.position minus transform.position. Alright, raycast hit, we need this to check if the hit, whatever got hit was the node that we're looking for. So if physics.raycast ray out hit. I'm not going to explain too much in detail about raycasting. If you really need to learn that, which you do for this tutorial, you should go over to the Unity tutorials and learn that, because it is an essential part in game development, I would say. So we're going to check the hit transform now. So if hit.transform is equal to n.transform, it is the object that we're looking for. So we're going to go neighbors.add_n. Alright, else it's going to continue. I think that's how it works. Yep, continue. Alright, now that we have a find neighbor script, that should find all of our neighbors. Okay, now let's go void on your gizmos. So gizmos is basically like, can I explain this? You know what, actually I'm not going to do gizmos right now. I'll explain that later. For now, when we add one, I can do a debug.draw line. So this will just draw a line in the editor while playing. So we're going to go transform the position to n.transform the position, and we're going to make the color yellow like it was in the preview, and I'm going to make it last for 2 seconds so we can actually see it. And I've spelled position wrong. Okay, alright, let's see if this works. But before that, we're gonna do this on awake. So we're gonna find our neighbors on awake. Alright, so let's check if this works. Save your scene just in case it crashes. And okay, alright, we have a little error here. What's going on? Why are these two not connecting? And let's check, shall we? Alright, well, this is odd. I pretty sure I added a box collider to all of these. I think maybe, what happened? Oh, okay. Well, they just didn't have a box collider. That should be the reason. If it isn't, I don't. Yeah, that is the reason. So they all need a box collider or a sphere collider, whatever collider you want, except for the 2D colliders. I'm not quite sure how to raycast with 2D colliders yet. I haven't gone that in depth into 2D. I'm more into the 3D side of Unity. Okay, so now we have a functioning node graph. We'll get on to programming the actual algorithm. I've gone ahead and created an A-star manager script and attached it to the A-star game object in our scene. Okay, let's begin coding the algorithm. As soon as we start, I'm going to go up top and add a using system.collection.generics to use the list and dictionary data type. Okay, once we have done that, I'm going to go add a dictionary of node type, and this is what's going to hold the parent nodes. Okay, so what I talked about earlier in the explanation, how each node is going to have a parent, well, that's going to be held inside this dictionary. So this node is going to be the actual node, and this node is going to be the parent of this node. Alright, so I did explain that in the explanation. It was a bit hard to understand, but you'll get it now. Okay, so now I'm not going to create a public void or any type of method. I'm going to create a public list, vector3, and this is going to be called calculate path. Okay, and it's going to receive a node start, node end. Alright, so this is going to be our function, which returns a list. So we can call this function and then we can get a list. It's very easy. Okay, now as soon as we start, we're going to add a list node called closed set goes, and we're going to create also a open set. I'm sorry if my keyboard is really loud. Okay, just a new one. And as soon as we start again, I'm going to do open set.add the start. Like I told you in the explanation, we're going to add the first one, and then we're going to sort through its neighbors and keep going over and over until we find the end. Okay, so node, and we're going to have something called the current node, and we're going to set this to the first object inside the open set. Okay, so we can't keep calling the calculate path over and over again, so to help us with doing the Pathfinder, we're going to use a while loop. So while the openSet.count is greater than 0, we're going to set the current node to equal to openSet 0. Okay, so the current node will always be equal to the first object in the open set. Okay, now we this is not necessary, but I like doing it just in case. We will add start.findNeighbors. So we'll find the neighbors of the start and end nodes, just in case, you know, it accidentally moves or something. We can always find it again quickly if we need to. Alright, now this is the most process intensive part. It's finding the one with the lowest F cost. So we're going to do a simple for loop here. So I is equal to openSet.count, I is plus plus. Alright, now here, we're going to if openSet, okay, yes, we do need a function for this, by the way. Alright, so we're going to create a little function here to help us. Int fcost, and we're going to get node start, node end, and node current. Alright, these are 3 values needed. Actually, even better, we'll go into the actual node script, and we'll create the integers here. So int fcost equal to node start, node end. I think this should work, yes. And we're gonna return, no, we're not gonna return anything yet. So int gcost equals node start, and int hcost equals node end. Alright, and we have to make sure all of these are public so we can access it from our A star manager. So why I'm doing this is basically so we can find the fcost and the hcost of all of our nodes, and it will be inbuilt into our nodes. Okay, so we're gonna return gcost start plus hcost end. Okay, like I said, fcost is equal to gcost plus hcost. This is basically what's happening here. Math. Okay, so return the gcost is gonna be an int. All of them are gonna be ints. So round to int vector3 dot distance between transform dot position and start dot position, and this will return a nice integer. This will return a nice integer of the distance, and I'm just gonna copy paste this and gonna change the start to the end. Alright, easy. Alright, now that we have this, we can go straight into the A star manager, and we can go if openset I dot fcost start end is lower than current node dot fcost start and end. Alright, if it's lower than that, yeah, then it should be set. Okay, so yeah, alright, if it's lower than that, or if openset I dot fcost is equal to current node dot fcost. I'm just gonna copy paste this. Sorry, this is the one part in the code that I really don't like. And openset I dot hcost end is lower than current node dot hcost end, then current node is equal to openset I. Okay, so we've just found the one with the lowest fcost, and if the fcost is the same, we use the one with the lowest hcost, so the one closest to the end. Okay, now that that's complete, we'll make sure if the current node is equal to the end, then we will actually end this. So return, and we'll return null for now, but I will print found path. Okay, so we will know to ourselves that we have found the path before I reconstruct it using the parents. Okay, now that that's done, we'll do this part, closeset.add current node and openset.remove current node. So this is the part where we exterminate the infinite loop between two nodes. So once we find a node, the previous node will be taken out, so we don't go back to that node again because it's a better option. Okay, so now that that's out of the way, go for each node n in current node.neighbors. So we're gonna find every neighbor in the current nodes list. Okay, and once we do that, we're gonna check if closeset.contains node. We're just gonna continue. We don't want this because it's already in the closed set. Okay, all right, now we're gonna create this integer called the tentative gcost. Okay, so the tgcost. All right, and we're gonna call the current gcost. All right, so the current node's gcost plus the distance between two nodes. So this one should be fine to do here. So we get this between node A, node B, return math f dot round to int vector3 dot distance between A dot. So basically we have to get the distance between these two nodes. The autocomplete. Why isn't it autocompleting? Okay, that was very weird. Plus dist between the neighbor, so n and the current node, I believe. Yes, it should be. Okay, so now we're gonna say if openSet doesn't contain n, we're gonna add it to the openSet. So openSet.add n, and else. Alright, yep, sorry, it's an else if. Else if tentative, so tgcost is greater or equal to n.gcost start, then continue. Because if the gcost is higher, right, than our neighbor's gcost, we don't want that because that's like a longer path than we need. Okay, so that's good. Alright, that's all good. Now this is where we set the parent of the object. So if basically at this point our pathfinding is done. It should say found path, or like at the end we'll just add here print path not found. Alright, and we're gonna return null. Alright, but we just need to set our parents. So if parent node dot contains key n, parent node n is equal to current node. So basically we have our dictionary and we don't want to overlap on the parent. So we're setting the parent of n to the current node. Okay, so the current node is the parent of n. If it already contains the key, then parent nodes dot add n and the value is current node. Alright, so that is done at the point. If I play it now, it should say found path. We'll just check that it does and it doesn't crash. If it crashes, we've made a mistake. Okay, so first actually, for that, we need to make sure we have something to actually run this script. So in play, we're going to add a star unit. I'm going to open this guy up and we're going to quickly, using system.collections.drag. Alright, I'm going to go firstly void start. Alright, we're going to add a quick void start and go a star manager, and manager is equal to get, game object of find object of type a star manager, so you'll find any a star manager in the scene, and manager dot calculate path, and this dot get component node, and let's quickly add a public node end. Alright, okay, now we can go end, and if we check now and we just quickly add a end node to him, which is this guy, the target, let's drag the target into the end. Let's save, just make sure it doesn't crash, and we have a found path message, which means it's working. Now we just need to retrace the path and we basically have finished. Okay, let's quickly do that now. Okay, well, this is the easiest part, I would say. So list vector3 reconstruct path. And before I continue, I just want to say where I got all of this pseudocode. So I didn't come up with all of this by myself. I got it from Wikipedia. A star. So if you go here into the A star search algorithm, you have this pseudocode. It's not code really, it's just tells you what you need to do in what order. It's not completely correct. I've changed lots, including the neighbor script I came up with, and I had to change a lot because that was a bit complicated and I didn't like that. So I changed it a bit, but it's on the same basis. So let's reconstruct path. Okay, we're gonna add a list of vector3, which is gonna be our placeholder for that. Current path is equal to new list of vector3. Okay. Now node current node is equal to end. So we're gonna start at the end node and find the end's parent and then the end's parent, and we're just gonna loop back all the way until the current node is equal to start. So easy way to do that, if while current node is not equal to start, I think, yeah, while current node is not equal to start, carpath dot add current node dot transform dot position. See how we're not actually adding the actual node, we're adding the position, because that's we don't want to add the node because it takes up extra memory when you're converting it from a node to the position later in the gizmos. So the current node, now we're going to set it to parent node current node. Okay, so we're going to set it to its parent. Okay, alright, now if carpath.contains start.transform.position, we're going to add the start. We're doing this because it stops as soon as it starts, and it doesn't add the start. So we're gonna add the start, and the most important part, we're gonna reverse it so we get the path in the right order, and we're gonna return this. Okay, so once we've done that, once we found the path, we're gonna return, instead of returning null, we're gonna return reconstruct path start end. Alright, easy. Alright, so basically we're done now. All we have to do is represent this, which is extremely easy. I will say that. Okay, so list vector3 path equals new list of vector3. Alright, and all we have to do is path is equal to. Alright, that's all we have to do. Void on draw gizmos. Alright, this is another really easy part. So if path is not equal to null, and if path dot counter is greater than 0, then we'll go for int I equals 0, I is lower than path dot count I plus plus. Alright, so we're gonna loop through the path and draw little simple gizmos to display the path. Gizmos dot draw, color equals color dot red. Alright, gizmos dot, okay, so if I is equal to 0, continue, else if gizmos dot draw line from path I to path I minus 1. So this should draw the correct lines and everything, and they should all be working. Let's see. Okay, we have a little error here. Carpath, oh, sorry about that, dot add. Alright, let's go. Should be working fully and functionally right now. Wait for that to disappear, and voila, we have it. It won't update automatically. That's because we need to put it into the fixed update if we want it to do that. Yeah, if you want that, we could you can put in the update, but I would rather put in the fixed update. It's a bit smarter to do so. If we check now, see, oh yeah, you might want to turn off the finding of the neighbors, but it does work. You can see the red line. If you want proof, here you go. Let's comment that out, and I will show you that it works 100%. Alright, doesn't matter where you move it. Oh, yes, this won't work. Why? Because we have to make another simple function before we can use it. And what is that function? Well, it's public void find all neighbors. So we have to, okay, so I wouldn't recommend this, but you can. I would only do this very sparingly, but okay. End of find neighbors. So this would just find neighbors for all the neighbors. Okay, so very easy. Gizmos.drawLine. Alright, so I wouldn't do this over and over again. In fact, I won't if input.get mouse button down 1, I will do this. Okay, so this one, I don't know why I have there. I'd start. So that little error that you saw there, how it's going down and like that, this will be fixed as soon as you see right here. There we go. If I go here, there we go. See, it's working 100%. And I'm gonna take a short break, and then I'll come and teach you how to make the player follow this path all the way to the end, which will take, I bet you, less than 5 or 6 minutes. Okay, finally it is time to make our player follow the path that we have created. But before we do that, here, when we add this, when we make the path, we're going to manager, before we actually use the path, we're going to manager to find all neighbors. Alright, that's pretty self-explanatory. And now we're going to add 2 floats. Okay, so public float close enough and public float movement speed. So movement speed is how fast it will move from one node to another. Close enough is basically how close you want the player to get to the object before you want it to stop. Okay, now let's get right into it. We'll create a simple void called start following. Alright, and after that we're going to go stop all coroutines. So if it's already following a path, we want it to stop and follow a new path, okay? And we're gonna create a simple boolean right about here saying bool reached equals true. We need check if the player has reached the target, okay? So we're gonna set the reached to true so it doesn't trigger as soon as it starts. And we're gonna go start coroutine follow path. Okay, so we're gonna make that now. So enumerator, you should study up on enumerators and coroutines. They're all the same and they're pretty useful when it comes to game development. Okay, so we're gonna check if the path is null or if the path doesn't have anything in it. And if it does have something in it and it's not null, it's gonna go to the next stage and it's gonna for loop through every node or position in that list, and we're gonna set the reach to false because it hasn't reached that area yet. And while reached is not equal to true, we're gonna make sure that it won't go to the next position unless it has reached that position first. So we're gonna go yield return null. So basically it won't do anything until this condition is satisfied. So vector3.distance between transform.position and path I, right, is lower or equal to close enough. If it's lower than that or equal to it, then it has reached the target, and therefore we can continue on to the next position, or the next point in our path. If it hasn't, we're going to make a simple direction. So vector3.normalize path I minus transform.position. I'm going to times this by our movement speed. Alright, that's easy, right? Okay, now the easiest part, transform.position plus equal direction. Alright, that should easily just move our player in the way. Okay, now all we have to do here is add a start following method, and should be good to go. And make sure when you're here, set it close enough and movement speed minus 0.1 and 0.2, and this should work. Let's check. Right click, works. Now let's move the target, see if it works, if there's any errors. There we go, it's all perfect. And this is only working because of the function that we created called manager.find all neighbors. Okay, this is the only reason it's working, or it's not going to work. Okay, that's basically it for the pathfinding. And basically what you can do now is like create new nodes wherever you click and like make the player follow. The possibilities are endless with A star. Like, it's amazing what you can do with it. Hey guys, I've had so much fun working on this project, learning A star at such a young age for me, and it's just been such a great journey for me. And I just want to thank you guys for getting me up to 100 subs. It really means a lot for me. And if you want to see more videos with more effort put into them, like this video for example, leave a like and a sub and comment on what you want to see next. I'll see you in another video.